Hi everybody, this lecture is for Wednesday the 14th of January. This is class number 2 of hydraulic engineering. Just as I begin here, I want to remind you of the suggestion to get a copy of the textbook. Now, it's not available in our bookstore. I don't think they were able to get any copies because it's out of print. But there are other places where you can get a copy. It's available on eBay, AbeBooks, Amazon. So you won't necessarily need the book for homework assignments, but as a reference and as a resource, it is valuable. So I'd recommend that if you can get your hands on a copy, that you should try and do that. Then the other announcement to be aware of is that homework 1 is due on Wednesday, the 21st of January. You'll need to submit that by 11:59 p.m. So you've got about a week to work on that one, and as you've got questions, please feel free to stop by during my office hours. I'll be happy to help you out. Today's lecture is related to flow resistance and just some ideas having to do with shear stress and different empirical methods for estimating the effects of friction. And it comes from sections of chapter 7 in the textbook.
Here's some pictures of Lake Oroville in Northern California. And this lake has been in the news several times in recent years. And for a while, it was kind of a poster child for the effects of drought in Northern California. Because back in 2011, the water levels were relatively high after a couple of years of good snowfall in the mountains of California, leading to runoff. And so that allows for a lot of recreational opportunities. It's great for water skiing, houseboats. They use the water for irrigation. But then just a couple of years later, in 2014, here's the same perspective of Lake Oroville with the water levels basically decimated. And people who have houseboats, they may still be on the water, but they're really not able to go as many places or enjoy the water in the same way that they used to. Here's another perspective of the water levels having fallen over the course of the same period in Lake Oroville. So the story in California for a lot of years was drought, and it still is in Southern California. But Northern California has a couple of good years when it comes to snowpack and runoff. In fact, back in December of 2022 to January of 2023, the water level went up by 62 feet in this reservoir over the course of just a couple of weeks. And then more recently, in November of 2024, a similar thing happened. Over the course of 5 days, the water level in the reservoir rose by 20 feet. So when they have rainstorms in the mountains, or when they've got a lot of snow and then it suddenly warms, that can fill the reservoir really quickly. So I show you these pictures just to make the point that in hydraulic design, we have to be prepared for variability. We don't just design something for the average conditions, whether it's the average flow through a pipe or the average depth in a reservoir. We design the system to be resilient in the extremes, because it's the extremes that can stress the system, whether it's extremes in temperature, extremes in demand, or sometimes extreme age. A lot of pipes that get put into the ground, for example, wastewater collection, they're left in the ground for 100 years. And so we have to think about, if the municipality just has one chance to get this right, if they're putting the pipe in the ground, and chances are they're going to move on and forget about it for a decade or even a century, how big should the pipe be if we look into the future and think about the likely development in the area that that pipe is serving? So I just want to reinforce this idea of variability over time, that there are extremes that can stress the system, and so the system has to be designed to accommodate it. So that leads into another thing that happened at Oroville Dam back in 2017. By the way, this is the tallest dam in the United States. It doesn't look like anything special or spectacular, but it's the tallest at 770 feet from the base to the top. And it's a very large man-made lake in California, 3.5 million acre feet. And that unit may not be familiar to you, the idea of what is an acre foot. It's a foot of depth and an acre of area. So that's a way of describing a certain amount of volume. It's the volume of water that would occupy an acre of area and 1 foot of depth. So this reservoir has 3.5 million acre feet. So that's really a lot of water. That's not millions of gallons. That's millions of acre feet. So it's huge. And it generates electricity in addition to the recreational opportunities and being an ecological, kind of like fish habitat regulator, and being good for irrigation of agriculture. They also use it to generate electricity. So what happened in February 2017 is there was a lot of rain in the watershed upstream of this reservoir. And the water falls on the mountains and it flows over the surface of the mountains. Some of the water goes down into the soil. Some of the water gets drawn up by the vegetation. But some of it runs off and pools in the reservoir. So it was so wet in February of 2014 that water was entering the reservoir at between 130,000 cubic feet per second and 190,000 cubic feet per second. So that's the water going in. And now let's talk about the ways that water can go out of this reservoir. Water can go out through the hydropower system at about 17,000 cubic feet per second. So that's just, they've got a series of generators and penstocks. A penstock is a pipe that leads to an electrical generator. And that system can accommodate 17,000 cubic feet per second. There's a secondary river bypass that will take a little bit more. That's through the dam. And then this spillway here, it's a concrete spillway, can accommodate 270,000 cubic feet per second. And the depth of water, that water can start going over this this service spillway when it gets to a depth of 814 feet. And then if it goes beyond that, oh, that's a clue. When it goes beyond that, here, the water can go over the edge. If there's more water that can go through the power system or through the service spillway, then there's an emergency overflow. And they really don't want the water to go through the emergency overflow because it's just tearing up the hillside at that point. You can see that the service spillway is clearly an engineered structure. You know, it's going to dissipate and allow the water to go losing so much elevation. And at the bottom here, they've got these concrete blocks to kind of absorb some of the energy so that it doesn't tear up the stream too badly once all that fast-moving water exits this service spillway. But unfortunately, there were some flaws in the design of the dam, and water started going through the service spillway, and it should be fine. You know, the service spillway can take 270,000 CFS, and there was only 190,000 CFS, and so it's within the design limits of the service spillway, but there was a problem. There was, with that fast-moving water, a little bit of scour that occurred, and the concrete cladding of the spillway got damaged, and once there's a little crack, it turns into a big crack, and a little bit larger, and the water's moving so fastly that cavitation can occur. These tiny little gas bubbles, it's actually liquid water. It's liquid water moving at a high velocity can sometimes vaporize and turn into moisture bubbles that then will collapse and send shock waves through the water. It can cause pitting and damage to propellers on boats and to spillways. And so there was a lot of water flowing over the spillway because, you know, the reservoir is getting so much rainfall, but then there was some damage that got progressively larger. And now think about it. They needed the water to go down this spillway because too much is coming into the reservoir, but they had to turn off the spillway because of the damage. So now the water level is getting deeper and deeper in the dam, and you know, some guys went down there to check things out. That gives you an idea of how big it really is. It doesn't look that big from this perspective. It just seems like, oh, what's this, maybe 20 feet wide or something? No, it's very, very big. So here's the hole. There's some guys climbing into the hole. And it was deep as well. We'll see a picture in a minute, but the problem is that the damage was on this right side of the service spillway, and it started scouring the hillside a little bit. people felt pretty confident that there's enough rock here that it's not going to get all the way to the dam. But at the same time, they were also feeling a little bit nervous because you don't want any of this rock to be scoured. It looks pretty solid, but it could be fractured rock, and if this is fractured rock in the hillside, then it can carry it away downstream, and is it maybe going to threaten the dam? So they started to evacuate people downstream, telling them, well, probably the dam's going to be okay, but just out of an abundance of caution, maybe you should move out of the path if the dam does break. And this gives you an idea of, the scour of the rock to the right of the spillway was headed in the direction of the dam. Still, it's got a ways to go. And spoiler alert, it never destroyed the dam. But they did end up having to send water over the emergency spillway, which they really don't like to do. By the way, this is just showing this brown color is just kind of indicating that material underneath the concrete is being washed downstream as the water's flowing over the spillway. So it should be all white and clear, but it's carrying rock and soil downstream as it continues to dig a deeper hole underneath where that service spillway used to be. So they started to realize that water was going to flow over the emergency spillway, which it had never done before. They only very rarely use the regular spillway. Remember, in Northern California, this water is precious. They don't want any of this to go to waste, so they keep as much in the dam as they can, and they just release it very slowly, enough to keep the fish alive, enough for the farmers to irrigate their crops, and so they're very rarely going to send water through the regular spillway. They can't harness any electrical power for what they send through the regular spillway, and they've never, like I said before, used the emergency spillway. So when the water levels were rising high enough, eventually the water did go over the emergency spillway. And you can see it's just this big brown streak where a lot of the vegetation that had been in place got washed downstream. I think this picture was taken actually after the flow rate was even higher before this photo. So it's hard to see why the hillside would be quite as decimated as it is. It's because the water flow was even greater than when this picture was taken. So they had water going through the electrical system to generate power. They had water going through the service spillway, although they were trying to keep the flow rates relatively low to limit the damage to that big hole. And then, in spite of those two also carrying flow, it started going through the emergency spillway. So there was a lot of people assuring us that the dam would not collapse, that it would just, the emergency spillway would be on the opposite side of the service spillway. Here's the hole. And it did. The dam did not collapse. The water that flew through the emergency spillway relieved the incoming flow, and then it stopped raining, and so the water level stopped rising eventually. After doing quite a lot of damage, more than $1 billion worth of damage. But these things are expensive. This gives you an idea that was pretty torn up by the end of it. There wasn't much left of the original service spillway. And look at all of this material which had been excavated by that water. A lot of power in the water got moved downstream. So the repair cost was estimated at more than $1 billion, and I ought to check in. I assume that project is complete, that they've built back better, and that hopefully next time they need to use it, it's not going to cause this catastrophic incident. But in a post-mortem analysis, the Association of State Dam Safety Officials said that this was not just a short-term failure, but it was a long-term failure to recognize and address the spillway design and construction weaknesses, that there was a poor quality of the foundation, and the service spillway was deteriorated. So some inspections in years prior to this incident had acknowledged the problems. It's not like it was a surprise. It was just that policymakers weren't acting on the concerns raised by the inspectors. And then, the inspectors, it's not necessarily in their interests to raise too much of a stink. They don't want to get fired for being a problem, So it's a tricky situation that raises a lot of questions related to engineering ethics and the duty to preserve the health, safety, and welfare of the public when you know that a dam isn't being maintained the way it ought to be. And I guess it's just lucky that there wasn't even more damage and loss of life than there was. Okay, so with that detour out of the way, let's just revisit our Moody diagram that we looked at on Monday. And remember, the purpose of the Moody diagram is to characterize the friction factor F. So the friction factor tells us the relationship between the flow characteristics and the viscosity of the water, and then how much roughness the pipe exhibits as flow is going through it, and therefore how much energy would be lost due to pipe friction. So just to summarize what we did in this example last time, we started with the relative roughness and the Reynolds number. Those two factors are what dictate the friction factor. So with the flow conditions, like the velocity of the flow, which we could get from the, in this case, just the given statement of 30 meters per minute. With the velocity and the diameter of the pipe and the given kinematic viscosity, that defined the Reynolds number for us. And in the example, it was 1.25 times 10 to the fifth. So that's the green line. The next thing we did on the Moody diagram is we looked at the ratio of equivalent sand roughness to diameter. And that's called the relative roughness. And in our case, if we divided the given case of S by the diameter, it turns out to be pretty close to 0.001, just slightly above that line. So the point of intersection between the relative roughness and the Reynolds number then takes us over to the left and intercepts the vertical axis, which is on the friction factor. And so the friction factor under these conditions is 0.022. And with that, you could then find out how much energy is lost as water is flowing through the pipe due to pipe friction. Does anybody have any questions about how to use the Moody diagram? Okay, so this is one of the problems on your homework assignment. And in this, you're going to have to determine the friction factor using the Moody diagram. That's just what we've been talking about. And then you're going to use the friction factor in this Darcy-Weisbach equation. So you're going to try and find out what is the, how high does the tank have to be? And so you're solving for Z1, because location 1 will be at the water surface in the tank, and the pressure of the water at the surface of the tank is 0. So P1 will cancel out. C1 will be the unknown. V1 is talking about the velocity of the water in the tank, and that's going to be 0. And there's no pump here, so the pump term will cancel out. So the only thing that's going to be on the left-hand side of the energy equation will be C1. And then on the right-hand side of the equation, you've got the elevation in this building defined as 100 feet, so that would be C2. And we're told that we want to have a pressure of 30 psi. So that'll be P2, 30 psi. So you'll have to convert that to pounds per square foot. It's in pounds per square inch right now. You'll need to express it in terms of pounds per square foot. And then I got a good question after class last time. This term here, gamma, gamma is the unit weight of water. And it's either 9810 newtons per meter cubed if we're in SI units, so that's the weight of the water per unit volume, or it is 62.4 pounds of force per cubic foot. So in this problem, you're working in traditional units, so you'll use the 62.4 for gamma in that problem. So basically, you're going to have to find out how tall should C1 be if you've got a certain amount of pressure you want to develop, and you want to deliver the water to a certain elevation in the building. So you know P1, you know, P1 is 0, C1 is the unknown, V1 is 0, so in this, it's telling you that the water's flowing at 1,000 gallons per minute. So 1,000 gallons per minute and then the diameter of the pipe being 12 inches is going to tell you what's the velocity of flow through the pipe. So the V in the Darcy-Weisbach equation, this V you get because, remember, if you've got water going through a pipe, Q equals V times A. So the velocity is the flow rate divided by the cross-sectional area of the pipe. So if I told you the diameter of the pipe is 12 inches, well, that's 1 foot. You can find the area of the pipe in feet. And then I tell you it's 1,000 gallons per minute. You need to convert that into how many cubic feet per second it is. You can find those conversion factors in the book or at various places online. Conversion between GPM and cubic feet per second. So you'll find the velocity, you'll find the F value using the Moody diagram, and you can find H sub F. And then from there, it's just substituting in and solving for Z1. So I just wanted to address that in this problem, where you're using the Moody diagram, you're going to be using the same process of finding the Reynolds number and the relative roughness. All right. And then, in case you don't have access to the book yet, let me give you the kinematic viscosity of water in these traditional units. The kinematic viscosity of water in traditional units, 1.22 times 10 to the minus 5th feet squared per second. You'll need that for the Reynolds number. 1.22 times 10 to the minus 5th feet squared per second. So remember, Reynolds number is velocity times diameter divided by kinematic viscosity. This is the kinematic viscosity that you can use for water in traditional units. So that's all I have to say about that. Okay, let's talk about resistance to flow. Think about water is flowing through a pipe, and it's experiencing a frictional resistance because the pipe is stationary, and the pipe has this roughness on the outside, and water has viscosity, meaning that water can't frictionlessly slip over some stationary surface. There's going to be a frictional resistance. So your book provides this diagram. You know, we're going to talk about this diagram for maybe 10 minutes. I needed to look at this diagram for a half hour to understand. Maybe some of you could understand it faster than that. Maybe some people take more time. But I raised the point just to reiterate how important it is for you to get the book, because, like, I'm going to tell you what I understand is going on in this illustration. But really, if you want to understand and thrive in hydraulic engineering, you need to sit and look at that at home, review these variables and the definitions, and really kind of do the force balance in your mind to understand it. So it's not enough just to sit in class and listen to me talk and then do the homework. That's not enough. What is enough is to engage on your own, to really think about the material. Have the book, read it, and sit there and think about it. So when I went through that process, what I realized is what this diagram is showing is a force balance in the direction of flow. So from location 1 towards location 2 is where the water is flowing. It's flowing from left to right in this illustration. So if the water is pressurized, and we do a control volume approach where we're saying we want to just take the water that's inside the pipe and look at the forces that are acting on that water. So we're going to pretend like the water that's outside of this particular control volume is an external force. So, like, water is continuously flowing through the pipe, but if we just focus in on one little section of the water, then the water that's to the left of that is pushing on the water that we're looking at. So here at 1, there's water on the left side that's pushing towards the right. So it's got a certain pressure acting over an area, and that acts as though it's an external force. Force is pressure times area. So water on this side is pushing the water that we're focusing on. It's pushing on it towards the right. And the same thing is true over here. is that there's some water on the right side of this fluid element that is pushing back towards the left. So those are both external forces. Then there's the weight of the water itself. And in this illustration, it's just saying, well, what if the pipe was inclined? If the pipe is inclined, then some of the weight of the water is acting in the direction of flow. Most of the weight of the water is down, but if you incline it, some of the weight of the water is to the right. And so that's in our force balance as well. And then the last component of the force balance is the pipe is pushing on the water in the opposite direction of flow. So if the water is flowing from the left to the right, then the pipe is in all directions, it's kind of like surrounding it. Can I hold your water bottle for a second? So here's the water. The water's flowing, and the pipe is pushing this way, but it's acting over the entire cylindrical surface. It's not just acting at a point, it's distributed over an area. And so the area over which that resistive force is applied is perimeter, so that's the outside length, and then L is the length of this fluid segment. So P times L is the surface of the cylinder, and the shear stress is the magnitude of the resistance that's being applied by the pipe to the water. And so if we multiply those things together, the shear stress and the area, it's a shear force. And so this is a force balance. You've got acting towards the right, pressure 1 times the area. Acting towards the right, the weight of the water, the inclined component of the weight of the water. So here, gamma times A times L. So A times L gives you a volume. That's the cross-sectional area of the pipe times the length gives you the volume of the water. And then multiplying it by gamma turns it from a volume into a weight of the water. So then sine of alpha is that component of the water's weight which is acting in the direction of flow, because this pipe is inclined. So this force balance is saying we can quantify all of these things directly except for the shear stress. The shear stress, we can't, there's no instrument we can stick into the water and measure the shear stress directly. We can measure everything else directly with either an instrument or a ruler. We can measure the area, the length, and so on. The angle we can measure. Shear stress is a little bit slippery. So let's rearrange this equation. What if the pipe was horizontal instead of inclined? Just to simplify this a little bit, if the pipe was horizontal, then the change in pressure exists only because of the pipe friction. Right now, as it's inclined, the change in pressure also is because of a change in elevation between 1 and 2. So there's two effects. If the pipe is inclined, there's the hydrostatics, which is accounting for some of the pressure change because of the change of elevation, and then there's also energy loss. But if we just make it horizontal, then the pressure change is described entirely by pipe friction. And there's this new term, R is hydraulic radius, and it's defined as the pipe's area divided by the wetted perimeter of the pipe. So if we have a circular pipe, for example, its cross-sectional area is pi d squared divided by 4. That's the area of a pipe. The wetted perimeter of the pipe is just pi d. So the perimeter is pi times d. And so hydraulic radius, area divided by wetted perimeter, is just going to be d divided by 4. Yeah. D divided by 4. If it's a circular pipe. Oftentimes they will be. If it's a circular pipe and the water is flowing full, then hydraulic radius is just diameter divided by 4. Okay, so where are we headed with this? We're just trying to understand what is shear stress. What is shear stress? And so if we know this force balance incorporates shear stress, and if we know that energy loss due to pipe friction is what causes the change in pressure, we can relate those two things. We can relate the energy loss due to pipe friction with the shear stress, and we expand that a little bit with our understanding of hydraulic radius. We can express it in terms of the length of the pipe, the diameter. So for a circular pipe flowing full, the hydraulic radius is d divided by 4. In the end, what we end up with is that the shear stress is gamma, which is the unit weight of the fluid, multiplied by the hydraulic radius, and then S sub F is the slope of the energy grade line. So the way that we define the slope of the energy grade line, S sub F is defined as how much head loss due to pipe friction there is in a certain length of pipe. So if you know the magnitude of the head loss in terms of meters, it will be given in terms of length. It has units of length. H sub F would be like meters of length. And obviously the length of the pipe is also units of length, meters. And so the slope is a unitless indication of the energy grade line. So energy grade line is something that we did in fluid mechanics lab last semester. EGL, you did a graph of the EGL on a couple of occasions. It is just simply the pressure divided by gamma plus the elevation plus the velocity head. So if you do like a graph of the three energy terms, that's the energy grade line. So it's this imaginary line that's above the pipe that shows how much energy there is in the water. So the slope of that, the slope of that energy line is going downhill to indicate a loss of energy in the direction of flow. The same thing applies in open channel. It's not just enclosed pipes only that experience these same effects. Resistance to flow exists in an open channel that's in contact with the air. So see this little triangle and the ripples beneath it? This is just kind of evoking the notion of a free surface of water above which is gas, like the Earth's atmosphere. So this is showing an open channel flow. The same thing occurs that we've got some inclined surface, the water's flowing downhill. We can do a force balance. There's hydrostatic force from the left, hydrostatic force from the right, cancels each other out if you've got steady uniform flow and the depth isn't changing. But the river is inclined delta Z, so like the bottom of the channel is inclined delta Z, and when you've got steady uniform flow, that's the same as the energy loss that's occurring. So if you've got an inclined surface that water is flowing over, what this open channel diagram is just showing that there's resistance down here. So the same shear stress multiplied by the wetted perimeter and the length of the segment, that is the magnitude of the energy loss. And so the reason why you're having a frictional loss in an open channel is because the bottom of the channel is resisting the water's movement. The concrete is not moving, the water is moving, and there's friction in contact between the two. Okay, so we talked about that for about 10 minutes. I think you should stare at this page in the book for about a half hour. So set a timer, just stare at it for a half hour and think about it. You'll make me the happiest man on earth. All right? Okay, so let's work an example related to shear stress. And because we're pressed for time, I think what I might do is just show you these calculations directly, because we still have some other ground. I got carried away showing you those pictures of Oroville Dam. So let me explain the setup here. We've got inclined, the pipe is inclined uphill, but you'll notice here that the energy grade line is downhill. And that's something that you should know, is it doesn't matter if the pipe is horizontal or inclined down or inclined up, that the slope of the energy grade line is independent of the physical slope of the pipe for closed conduit flow. The energy grade line is just a graph of the energy in the water. And so if the pipe is going uphill and you're losing pressure in the water because of that, you're also gaining elevation. So it's all kind of exchanged, and the reduction in the energy grade line is because of pipe friction, H sub F. Okay, so what we're told is the diameter of the pipe here, that it's inclined, so that's S naught, the slope of the pipe itself. And let's say, just for instance, that we somehow know the shear stress of the water is 45 newtons per meter squared. In a case like that, what would be the slope of the energy grade line, and what would be the pressure change over 100 meters of pipe length? So let me show you the calculations for this, and then let's see if there's any questions. I think I've got this scanned already. Might be just... Okay. I don't have the best handwriting. I'm working on it. Hopefully this will show us what we need to do in order to determine, remember, what we're trying to find out is the slope of the energy grade line, S of F. So what we would do in a case like this is use the diameter to find the cross-sectional area, use the diameter to find the wetted perimeter, and from that we can determine the hydraulic radius. And the reason why that's important is, remember, we had this equation that was saying the relationship between the slope of the energy grade line, here at the bottom, slope of the energy grade line, shear stress, hydraulic radius, and unit weight of the water. So those are kind of the four variables that we're putting together here to find out the slope of the energy grade line. The unit weight of water, just using kind of the standard 9810 newtons per meter cubed. A hydraulic radius, I could either use the shortcut and just say it's the diameter divided by 4, and from that get 0.0375. Or I could go to the trouble of calculating the area, calculating the wetted perimeter, get the same value, 0.0375 meters. So either way you do it, you get the hydraulic radius, we were given the shear stress, and we know the unit weight of the water under typical conditions is 9810 newtons per meter cubed, and so that tells us how steep the slope of the energy grade line is. So you're losing energy. Every meter of distance, you're losing 0.122 meters of energy in the water. That's how much energy the pipe friction is removing from the system for every unit meter of flow through the pipe. Okay, so that was the first part of the example. The next part of the example is, given that, what would be the pressure change over 100 meters of pipe length? So what we're going to do with that is remind ourselves that the slope of the energy grade line, here in this component of the formula, the slope of the energy grade line is the magnitude of friction loss divided by pipe length. So we're now going to be using this formula to answer part 2 of the example. What's the pressure change? We want to know how much head loss actually accumulates in 100 meters of length. So if you've got 100 meters of length, then your total head loss is going to be 12.232 meters of energy loss due to pipe friction. So if you're losing 12 meters of energy due to pipe friction, and we put it into the energy equation to account for the elevation difference, because in 100 meters of length, then the distance downstream is going to be, the pipe is elevated 10 meters. So if we just say C1 is 0, C2 is 10 meters, so we want to know what's the pressure downstream. The pressure is changing for 2 reasons. It's changing because of the energy loss due to pipe friction, and it's also changing because of the elevation difference. And both of those are going to be reducing the pressure. If the pipe downstream is higher, that means the pressure is going to be less because of the elevation change and because of the energy loss. So the magnitude of the pressure change would be 218 kilopascals over 100 meters of pipe. And that's a lot of pressure change. Just to put it in perspective, your typical house system, like if you've got typical water pressure in your house, it's about 500 kPa. So in a case like this, whatever flow is going through that pipe, the pipe might be too small. You know, if you don't want to waste pressure on head losses, you maybe need to make the pipe a little bit bigger to have less energy loss due to pipe friction in a scenario like this. So I apologize we had to rush through that calculation. If you're struggling to copy it all down, I'll remind you that the video is going to include this this portion of the PDF file. If you need to go back through the YouTube video, then you can copy the rest of the example. And hopefully have more time to think it through after class as well. Any questions about this example just relating shear stress and head loss due to pipe friction and pressure changes? So this is a good lead-in to that problem number 8 on the homework that I showed you the figure for at the beginning of class, because we're substituting in known elevations, we're dealing with the velocities, finding the pressure difference effect. Yes?
Since the slope is changing, the velocity should be changed?
Good question. The pipe confines the velocity. Because water is incompressible, the velocity is the same between location 1 and location 2. So let's say if here's location 1, here's location 2, the water velocity is the same because the diameter is the same. If the diameter of the pipe isn't getting any bigger or narrower, the velocity has to stay constant. Because water's incompressible. Its volume, the volume that it occupies isn't going to change based on the pressure of the fluid. A gas would maybe be different, but the velocity at 1 and 2 is equal. Great question. Are there other questions? Okay. So remember that there's a difference between the energy equation and the Bernoulli equation. They look similar. The Bernoulli equation is good for something where the diameter is changing and to predict the pressure change due to a change in diameter. So the Bernoulli equation would be good for a valve or a bell like this, but the energy equation would allow you to, for a pipe where the diameter is constant, know how the pressure is changing due to pipe friction. So the Bernoulli equation ignores energy loss due to pipe friction, but the energy equation accounts for it. So the change in pressure through a pipe is because of energy loss due to pipe friction. And so figuring out how big the pressure change is going to be is what we use the the Hazen-Williams equation for and the Darcy-Weisbach. Okay, in the time that's remaining, I want to just talk about a piezometer. This is probably the simplest way to measure the pressure in a pipe. Is if you've got a big pipeline and you just punched a hole in it, water starts spraying out all over the place. But then if you connected a tube to that hole that you punctured, and then you just run the tube up, eventually the water level is going to rise to a certain height, and then it's going to stop. So a piezometer is just a location where the water is rising to a height that corresponds to the pressure in the pipe. And so how high will it rise? Well, you just use the hydrostatic equation to describe the delta H. So it's related to the unit weight of the fluid. So if you have a piezometer at 2 locations in a pipe, then the difference in height that the water rises to is because of energy loss due to pipe friction. Even if it was inclined like this, if there's 0 water movement through the pipe, then the water level would rise to the same elevation. Even if the pipe is inclined, if there's 0 flow rate, then it would go to the same level. But this change of elevation between the piezometers tells us that the water is flowing from the left towards the right and that there's an energy loss there. So a hydraulic grade line is described by the physical location of the water in the piezometer. So you could visualize the hydraulic grade line with a series of piezometers connected to a pipe. And it's from this observed energy loss due to pipe friction that we can use the Darcy-Weisbach equation to estimate what the friction loss would be. Because, we can physically install a piezometer, but we want to be able to predict in the absence of direct measurement how much pressure change there's going to be. So we use this Darcy-Weisbach equation to predict in the future how the pipe is going to behave in situations that we don't necessarily want to install a piezometer at every location in the system.